Thank you. Thank you. So thankfully the title's long enough that it'll take care of the upper portion of the blackboard if it's possible. This is joint work with Peter Lapp. But first I'd like to thank Manish and Stephen, if I can spot him. Thank you. And Anne-Marie and Alan for organizing this conference and for the opportunity to be here. It's been really great for me mathematically, as you'll find by the last board if I get there, and also personally, it's been really fabulous. Thank you. All right, so we've been talking a lot about types and so forth. All my representations are complex, and I really meant to put the keyword tame here. All I'm doing is tame. So G is like everybody else, non-Archimedean, a nice group over a non-Archimedean field characteristic, residual characteristic P. And the kind of question you'd be looking at is, well, if pi contains a type, which we assume that everything is going to contain a beautiful type, is it unique? And the quick answer is no, of course not. It can't possibly be unique. If I have one type, I could conjugate it by G, and I'm going to have another type. So you've got whole conjugacy classes of these things. Even worse, imagine you've got a type for a compactly induced representation of supercuspidal. You could just induce it a little bit further up, and then you'd have another type on a bigger group. So that's not quite the question that we're asking. So when we say unicity, which is Cuspidus's word, I think, we mean something a little bit more careful. So is there, so unicity would be the statement, at most one type per conjugacy class of maximal compact subgroup. Okay, and we saw, for instance, in Colin Bushnell's lectures, we saw that for GLN, Pathological showed that this was exactly true. In his work in 2005, he showed that all supercuspidal representations, and this is what Professor Bushnell called the p-types. And that result was really important because it helped us see that of all the types that you could have, there were no unexpected ones in this case. Every type was exactly of the type that we had already seen and become familiar with. So this unicity result was used in that sense. But we've also learned from Alan Rush's lectures how important types are to understanding the Bernstein components, to understanding Hecke algebra isomorphisms. We've been talking about those aspects in Anne-Marie Aubert's lectures, also about a possible inertial Langlands correspondence, which is Peter Lapham's interest in this subject. So having a handle on the set of types is something we really like to do. And a nice way to do that is, well, if you had this kind of unicity, and of course I do have to do per conjugacy class of maximal compact because unlike GLN, I'm going to have lots of maximal compact subgroups. If I had a handle like this, I would have a much more tractable set of types to work with, perhaps to write down better correspondences. But immediately you realize that the situation is going to be more fun than that. GL2 was in fact what Hinier worked out in 2002. He did it completely. It's hard to find, unless you already know, an appendix to a paper by Breu and Gazal about mod P representations, and now we understand why it was there. And in here, he was working on all the types on the maximal compact subgroup for all representations of GL2. And he has an example when Q is equal to 2 in some kind of principal series representation such that there exist two non-isomorphic types. So I guess I want to call them maximal types. And I hope that's not confusing today, but that's the shortest word I can think of that would evoke this idea of a type living on a maximal compact subgroup. There's other words out there, archetype, that's been used, anyway, it just gets crazy. So this is just saying, so we don't have unicity of type in this case, but that's principal series. You knew that things were going to go wrong with something that was non-cuspidal. In Alan Rush's lecture, he pointed out the Ewart-Worry subgroup with the trivial representation, that's a type for some reducible principal series. But if you induce that up, and you look at your maximal compact and a trivial character, or the maximal compact and the Steinberg, neither of those is going to be a type, because although they identify the Bernstein component, they're not going to give you like a progenerator, because they don't occur in all the different irreducibles in that Bernstein component. So we already know that for, well, I'll squeeze it here, for non-cuspidal, we look at typical representations. And that would be something that identifies the Bernstein component, but is not kind of like the progenerator. And people have been working on the non-cuspidal case. I'll just say a couple of words here because they are here at this conference. So Santosh Neddampally did a lot of GLN. I'll just say a lot. I mean, that's a very, very big question to answer, and he's been looking at that kind of unicity. There, the question is about, do we at least know what all the types are? Are they just the ones that we expected to see? And then very recent work, I understand that Neddampally and Amiya Mandal are working on the classical case. So this is in progress. And that would be looking for the same flavor of results. I'll plug myself. I was looking at SL2 and understanding the principal series, and I was really interested in all the branching rules, but from that you can kind of pick out what's happening about unicity of types or typical representations there. And just to mention some nonlinear groups, Cornelia Karamian-Poor, in her thesis in 2016, was looking at n-fold covers of SL2. So that's not metaplectic covering, but more fun than that. And looking at the principal series there and understanding what kind of branching rules you'd be getting, from which she can infer something about the analogous question for this nonlinear case. Okay, but we would like to talk about the supercuspidals, because those are fun. So the supercuspidals. So there, I've mentioned already some stuff happening with GLN. SL2, well, so I was looking at that from the perspective of writing down the branching rules in around 2013, but Peter Latham considered this as the first case in his thesis by completely different means in 2015, and here we're getting some kind of unicity. Ooh, P greater than 2, if I don't say it. Then Peter Latham also looked at SLN, the essentially tame. And then for G general, so connected, reductive, depth 0. So these are Peter Latham. And in all these cases, you have a unicity result. Actually, in the connected depth, in the depth 0 one, it's really nice. So you could have a lot of maximal compact open subgroups, and they're not all attached to vertices of the building. But what happens is that if you're a depth 0 representation, you're attached to a vertex of the building, and that's the only maximal compact that can carry one of these maximal types. So it's a very clean and crisp result about exactly where you can find your types. They can't show up anywhere extraordinary. So, all right. So I guess I can get into my hypotheses for today. Maybe I can squeeze one up here. So my first one is my G is going to be semi-simple and simply connected. And as I've already mentioned, I'll be using the building, and those are the nicest hypotheses to have if you're going to work with the building. And then the kinds of representations I want to look at are positive depth, toral, tame, toral, supercuspidals. And what I mean there is following this other family of constructions. So, construction, and then a whole bunch of work leading to Jeff Adler in 1998, and JKU in 2001, and then there's more things to say after that. But that's the family of things. I'm so happy to join yesterday for doing this great presentation, explaining exactly how you correspond the two kinds, so we're all set to talk about this version of constructing supercuspidal representations. So I should mention, so there are definitely two languages in our field, aren't there? So we can speak about these and how to construct them in the Bushnell-Kutzbell language, and then we also have from the JKU language. So it's been really fun to work with Peter, who speaks the opposite language. Our conversations are hilarious, but somehow it's been really, really fruitful because obviously it's between those two worlds that we really understand what's going on. Okay, so I guess I want to kind of recall how this works. You saw yesterday that JKU datum would be a whole bunch of information. With these two hypotheses, then my datum is just going to be a pair. So I'll call it capital Psi is G arrow, phi arrow, where, so G arrow, that's going to be the sequence of twisted Levy subgroups. And in my case, I'm starting with a torus, that's the toral adjective. And this is contained not equal to GY up to GD, which is G, a sequence of twisted Levy subgroups. Which split over a Galois, thinly ramified, extension, let's call it T over F. And then in this, I'm saying that T is an anisotropic torus. Anisotropic is also maximal torus, because it's supposed to be Levy subgroups. So twisted just means that if you went to E, then this would just look like a sequence of Levy subgroups. And then because I've got an anisotropic maximal torus, then you can be looking at the building for G over F, and you could be intersecting that with the apartment for the torus T over the extension field. So for the extension field, this is just some other regular happy apartment. And then when you take the Galois fixed points, you'll be ending up with exactly the apartment corresponding to that torus over F. But because it's anisotropic, this is just going to be a single point. So we can think of an anisotropic torus as being attached to a point. And I might as well, without loss of generality, my X is going to be in the fundamental alcove in my favorite standard apartment. So that is to say, everything we do today, we immediately go to the standard apartment. We don't have to do anything too crazy. All right. So that's the G arrow sequence in here, of which our only interest in today is mainly going to be this first piece. This phi arrow, this is a sequence of characters, phi 0, phi 1, up to phi d minus 1, where phi I is a gi plus 1 generic character of gi of depth ri. Okay, so depth ri for a character, so this was just like the level, it's the idea, remember, this just means that phi I on gi x comma ri is non-trivial. So at the ri level of the Moicroside filtration, this value is going to be non-trivial, but as soon as I get a little bit further, so gi x ri plus, this is trivial. Sorry, that's a bad way of saying it. That's all. And then with Moicroside filtration, sometimes if you haven't met them too much before, it's just exactly like the G0. Let's see here. The X here, this corresponds to the hereditary order that we were learning about, and this G0 or T, so in the general case, this would be the A centralizer of the field extension E. The field extension E is kind of like the torus T that we'd be talking about. And then your hereditary order has a period, and in the Moicroside filtration, that's just been normalized to be period 1, and so these RIs in general are like rational numbers. Those are the interesting ones we care about. Okay, I'm also going to use the notation SI is RI over 2, and we saw how that came up in Professor Bushnell's lectures when we had the difference between 1 plus M over 2 and n plus 1 over 2, the floor function of those two things. That's the difference between SI and SI plus. That's how those things will show up for us. Okay, and so if we have all that, then, oh, darn it, that's not the thing to erase, but I'll write it again. So given all this information, we can construct by a fabulous procedure that in fact we don't need to know very much about today. Then there is an inductive procedure, an inductive construction that gives, well, first off, a representation kappa, which will be like a kappa 0 times a kappa 1, kappa d minus 1. Of the group, my group, I'm sorry, is going to be capital K, but it's really like the J upper 0 beta alpha, beta A that we had. And this would be like take the first piece, which is the torus, and then construct the Sears tower that Jen was drawing. So G1x comma S0 times up to GD, which is just G of x S D minus 1. And this one is the highest level of entanglement at depth 0, but all the other ones have been pushed down, but they're getting larger and larger, and that's the Sears tower effect that Professor Bushnell was talking about, and that Jen drew. All right, so we get representation kappa of this group K. And just to mention, so the inductive part is, so K0, kappa 0 is a representation of these two groups here, and then it's just extended in a natural way by the complement. Jen talked a bit about that, it's an inflation. Kappa 1 is a representation of the first three pieces up until kappa d minus 1 is a representation of the whole thing. But you just kind of keep inflating. So and each of these depends mostly just on the local piece of the phi I in here. Okay. And of course, that would be our type. And pi psi, which is the compact induction from K to G of kappa, is an irreducible supercuspidal representation of G of depth R is equal to this RD minus 1. So a few things are a bit simpler and nicer here because of our hypothesis number 1 up there, just to mention. Okay, so we have this construction, and this is what we call our tame supercuspidals. It applies quite generally. We know exhaustion due to Kim if P is large enough, for example. What we'd be looking at, though, is we want to understand something about types, so we care when two data would give us the same representation. And so there's a proposition by Hakim-Murnaghan. Which was an application of working with distinguished representations that we heard about yesterday, 2008, I guess. And so in general, it's quite a bit to write down. It involves renormalizations and refactorizations of these characters that we have. But for the toral case, it's quite lovely. So if psi dot equal to G arrow dot phi arrow dot is another cuspidal datum, another toral datum of the restricted kind that I'm talking about, then pi psi will be isomorphic to pi psi dot, if and only if there exists some G in G such that T is the G conjugate of T dot. Sorry, of course, T dot is the first torus in my G arrow dot, and this part's really nice, if you take the restriction to T of phi 0 to phi d minus 1, so just the product of all your characters restricted to the very smallest T in there. So retaining very little of everything in here. This has to be equal to the restriction to T of the G conjugate of phi 0 dot to phi d minus 1 dot. I mean, you can't get a much simpler kind of equivalent statement than that. So part of this was also my sales pitch for if you're trying to tackle the JKU construction and get familiar with what looks like a daunting task, the toral supercuspidals are a great way to start because you can just focus on some really nice stuff and the answers are quite simple. So I guess that's how it worked out that Peter and I we're working on the difficult cases as well, but this is the one that kind of gave us a sense of the shape of results to come. Okay, so I think, oh right, then I want to do a corollary of this, which will be interesting to us. And I better copy it down. So we have psi as above. Suppose that I choose psi, a character of t, of depth less than S0, S0 being this first level of the filtration. So I'm choosing a character that really is only going to see the t part of this. It's not even noticing the rest of this Sears tower because it's so short. So that means it's trivial on t as 0. Then I can construct psi dot, which would be the same group sequence, and then for my character sequence, I'm just going to modify that first character. So the first statement is, this is a datum. The only thing that you would want to check is the genericity that's over here. That's the only thing that's not completely obvious. But it is obvious as soon as you realize that being G-generic is a function entirely of this restriction to this last piece where it's non-zero, which is way down at R0, and we're only modifying our character way up at S0. So there's no question about this guy being G-generic, so that part's easy. And let me just say here, right, the kappa dot that you would get from this new datum here is just going to be psi bar times the kappa, where psi bar is this inflation that I mentioned briefly from t to k of your character at psi. So that is to say, the inducing representation is related in an equally simple and wonderful way. So this is the simple case that I really want to talk about today. You can see that my strategy would be to say, well, if psi is a non-trivial character like this, then I'm going to have an inequivalent supercuspidal representation. And if I have an inequivalent supercuspidal representation, maybe I can use that to make sure that something else I've got in my hands cannot contain a type. It's convenient to leave 1 and 2 up for anybody who's going to criticize all my broad statements that are completely wrong in the more general case. So we're doing this, so next we're going to do branching laws. And then full agreement with Professor Prasad that this is a very fun thing to look at. This is the most interesting stuff out there. And that's basically what we're doing. We're going to restrict this maximal compact, and we kind of want to see what shows up. So in our case, maximal compact subgroup, subgroups. And this is my hypothesis 1 that's helping me out briefly, will be stabilizers of vertices in the building. And that's gy, and y over x. And so I'll be fixing y throughout, and then I'm talking about the restriction to gy of the representation. So what I want to do is take my representation, my supercuspidal, and I want to restrict it to the maximal compact open subgroup gy. Well, we're going to do Mackey theory, which says, oh, no problem at all. This is double cosets gk induced from gy intersect the conjugate of k to gy of some conjugate of kappa. Okay, so this is clear. Your Mackey restriction, you certainly don't expect these things to be irreducible or anything, but at least it's giving you some kind of decomposition, and now your job is to kind of knock off a lot of those pieces and say they can't possibly contain any types, and that's how you'd be aiming to get to unicity. So this is lovely, but this double coset space with a k here, this is horrible. I think the whole reason why representation theory of groups over these kinds of groups, compact open subgroups with p-adic groups is so horrible is because this double coset space is not one you want to consider. What's the problem with it is that GY is completely related to our favorite standard apartment. It's a lovely group. But this K has this toral piece. And that toral piece that's still here, this one honestly belongs somewhere else. And we just, they just are not compatible in a nice way. So understanding this, or more generally for a twisted Levy sequence, I mean, all the pieces that show up in here are twisted levies, so these two groups are kind of incompatible in a lot of ways. So we're very sad about that. But to the rescue, we notice that K is contained inside of the stabilizer at X. Now, why is that true? Because T is a point associated to X of the came force. I'm telling you that T is contained in GX, and then all of these, by definition, are contained inside of the stabilizer subgroup GX. That's how this all works out. Well, now that's fine, because if you look at the double coset space GY, G, GX, well, this by Bruhat-Tietz is really just WY, WA, WX. So this is the affine valve group, or the extended affine valve group, same thing here. And WX, this is the group generated by reflections in the walls containing X. All right, so same thing for Y, of course. So that is to say, this double coset space is perfectly reasonable, and we can describe it by something in the apartment. We like that because this means we'll be able to picture what's really going on. So to say what this space is, we just scribble a quick example. So if Y was hyperspecial, that's a nice vertex. I'll draw a picture in a moment. Then that would mean that WY is just your finite valve group. And so your affine valve group, like your finite valve group, that's just your co-root lattice. And then you're modding by WX all the reflections in the facet through X, right? So you're just going to get the positive cone for X. So and what we're talking about here is co-root lattice intersects a positive cone for WX, and in a way that you can make perfectly precise. So I can think of my coset representatives as being elements of the affine valve group. Specifically, I can think of them as being like co-roots in general. I don't need to do hyperspecial.
Both WX and WY are finite valve groups.
WX and WY are finite valve groups, yes. Okay, so this is great, but well, now I'm dealing with these big double cosets. So in general, just a note. So in general, I'm looking at some double coset like this, and that would be over certain values of L and GX. It would be double cosets of the kind that I really need to consider for my Mackey decomposition here. But now this is really quite nice because you've got L is stabilized in GX. And so this pair KL kappa L, that's going to show up as the actual interesting data when I insert an L here. Then the thing that I'm considering, this corresponds to this other data conjugate of psi in a naturally defined way. So what this is saying is that up to bearing in mind that I might have to be thinking about GX conjugacy classes of my datum, I can just pretend that L is equal to 1. So that will come up and bite us, and I'll try to sweep it under the rug and see if anybody calls me on that. But basically, it works out fine. So up to GX conjugacy, we're just going to assume L is equal to 1, and then at some point we won't be able to do that. So I'm sorry, I'm making that be a bit sloppy. Okay, so I think then I'm ready to say, right, and so we're going to consider a specific Mackey component. That's what I'm going to call it. So I've picked an element G. I fixed G, so maybe I'll call it tau G in case I need that. And it should be one of those guys. I don't really want to work with the conjugate of K and of kappa, so I'm just going to conjugate this whole thing by G inverse, if you'll permit. So the representation that I'm interested in is, okay, so I'm going to conjugate gy by g inverse. G inverse acts on the apartment, so it's going to send the stabilizer of y to the stabilizer of g inverse y. Same thing down here, g of g inverse y intersects k of kappa, and that's a much more friendly thing for us to work with today. Okay, so these are the ones that I want to understand completely, and this is the right time to talk about the building. Sorry, I thought that'd be a really funny time. Okay, let's do SB4. Oh, right. So there we are in SB4, and here is my fundamental alcove C bar, or C if you want. And then we had that the stabilizer, the Galois fixed point coming from our torus, was some kind of element of the building, which did not need to be a vertex. In fact, very rarely would it be a vertex. Say if you were maximally unramified torus, then you might, oh no, you have even worse than that. But anyway, that's fine. You have some element X in your building, and then you are looking at a point y, which is going to be a vertex. So for example, if this is y over here, my very favorite hyperspecial. So the hyperspecial ones are the ones that look like they're supposed to, and then this guy over here is non-special, because it definitely doesn't look like it's supposed to, and it'll come up later. Then we're looking at taking, this one's hyperspecial, so really I'm just going to be conjugating all over the positive cone for x. So I might get this guy over here, this might be my g inverse y, or maybe this guy would be my g inverse y. Those are the kinds of things that I could have. Okay, so now let's understand what this intersection, well, not that one, this one over here. Let's try to understand what this intersection is all about. Because if we can understand this intersection and what kappa restricts to, then we've got some mileage of things to go. So what we can do is K intersect G inverse Y. Now, K is contained inside of Gx, as I mentioned. This is important. And now, hey, cool thing about buildings, if I stabilize X and G inverse Y, then I have to stabilize the whole line from X. Sorry. To G inverse Y. So here's two different cases and scenarios of stuff that could happen for me. So this stabilizer here is the stabilizer of the line. So it's lines right here. Okay, so I'm stabilizing this whole region here. Oh, cool. If I stabilize this whole region, then for any point Z that I would like that's on that segment, I have this is contained inside of Gz. So I have a way of translating this to talk about a different point in the apartment. So Z in this. Okay. So the strategy really for making this a tractable question is to convert everything into questions about stabilizers with points in the building. So this is the first thing. And maybe I'll just point out that these are definitely different scenarios, and they won't matter too much for us. But notice that here, the stabilizer at this point X is the same as the stabilizer at every point along the line, up until I get to the vertex when it's bigger. And then it's something different when I cross into the next chamber. Whereas here, immediately I jump into something that was a smaller subgroup. And since we're looking at restriction to this kind of line, you see that those will have slightly different behavior. Oh, and if I need it, I guess I will call the facet that contains X, I'll just call that script F. For a lot of reasons that one might be nice to remember. Okay, so we're ready to kind of tackle what we want to do. We understand what representations we're looking at, and now we have a way of understanding this inducing subgroup in terms of the building. So we're going to have three cases. And, well, they're just going to happen. I mean, regardless of how much time I have. All right, so we have three cases. The first one is a really pleasant case, and that is suppose that Gx is contained inside of G inverse Y. This is easy to understand because X and Y are supposed to be on the same fundamental alcove, well, then this forces G to be 1. This is again my hypotheses. So certainly G has to equal 1. This is not an if and only if. For example, this vertex down here, the stabilizer here does not contain Gx up here. They both contain equal hori, but this is not if and only if. But if I have this scenario, then, okay, so Y is a vertex of script F. That's really what we've decided that we have here. So let's consider this as the most natural case. And then if you're looking, so I'm looking at this double coset, which potentially could have devolved into a number of actual double cosets of the kind that I need to consider. But G is 1 and Gx is contained in Gy. So this whole thing is just Gy, which is the same thing as Gy times K. So only one coset. Okay, so I just have one component here, and what is it? Well, I'm going to be inducing from K is contained in Gx is contained in Gt inverse Y, which is Gy, up to Gy of kappa. And so this guy is a type. And I can tell it's a type because if I just keep inducing all the way up, compactly induced from here up to G, I get my pi C. Okay, so this is great. These are the types that we're supposed to get. These are the ones we totally expected to get on a maximal compact subgroup. And my point is here, I should have gotten types there and there. All right. And we're also immediately seeing that I shouldn't expect that each type corresponds to only one maximal compact open subgroup. Certainly I should expect to get quite a few of them in general. So that's a nice feature. So I guess we're ready for case 2. So case 2 is going to be not symmetric. I'm going to say suppose that T is not contained in Gg inverse Y. So T, remember, I guess K was T G1 x S0, G2 x S1, G x SD minus 1. And so I'm not asking immediately about all of K, which is a very tough group to understand. I'm just asking about the toral part because asking stuff about the torus tends to be a nicer thing to do. So now I'm saying, well, just suppose that T is not contained in the stabilizer at that point. Okay, well, here we have our building, and here's our point X. T is contained inside the stabilizer here. T is not contained in the stabilizer here. The stabilizer is a bounded convex set, and therefore there is some point along this line, say Z, where T is not contained in that stabilizer. So I don't have to go all the way to the end. There'll be various points along the line that I can choose as I need, and T would not be contained in the stabilizer along that point. So, but what I really need is the following lemma, which is about, I understand how to think of T in terms of stabilizers of things in the apartment, but what about all these guys here? So this lemma is something I did for a slightly different role, but also think about wrenching rules. So suppose that S is greater than 0. Let's think about the set omega xs, and that should be all the points in my favorite apartment, such that for all my roots, alpha of z minus x is less than or equal to S. Okay, so this is describing some bounded convex region in my apartment. Maybe I should just draw it. So for SP4, you have 4 positive roots to consider, but 2 of them take over. And so if I have a point S, what's going to turn out is I have this little square of radius, I guess it's S over 2 or something, depending on how you count. That's the other roots just are redundant when you draw your picture, when you write down these inequalities for all your positive and negative roots. If you're in something like SL3 and you had a point X, then this region here would be some nice friendly hexagon around that. So it's an easy to describe kind of region inside of our apartment. And the statement is that GXS is contained inside the stabilizer of this region. So we're now comparing the multi-site filtration subgroup with the stabilizer of a subset of the building. And I might as well just mention, this is the definition gives us, and that's also the stabilizer of the closure. That's the simplicial closure, so all the facets that meet this guy. Cool. So what I just want to say is that this is giving us a way to understand these filtration subgroups in terms of fixed points, which is how we're understanding everything else. Now, if if you look at this, you might begin to say, are they equal? Well, no, this one definitely always contains the split torus, if you're a split group, for example, whereas this one, the torus you have shoved down to level S. But in the case of split groups that are, yes, split groups, simple, semi-simple, that don't contain a type of G2, you have no problem getting like an equality if you throw in the split torus here, or something nice like that. So it's not so far off. So this is good, and the consequence would be, so my TS, that's the S filtration group, so this maybe where my character would be trivial. This, by definition, is contained in GSS, that's how the Morphoset filtration works out. And then this, by what we're saying, is GXS. We do bars, so if Z is ever in the closure of this region of radius S around the point X, then I have that my torus, the X filtration group, will be inside GZ. I won't erase this. Cool. All right, so I think we can say our first proposition. All right. So here my psi and my g are given. And so that means that I might have L conjugated to what I had to begin with, but there we go. Now suppose the torus that I have is not contained inside of GG inverse Y. All right, so this is the case 2. But now I'm going to add an extra hypothesis. So suppose over S0 was R0 over 2, the depth of the very first step of your Spears tower, which is, I never heard that before until you mentioned it in your lectures, and I think it's great. So suppose, okay, Roger House, well, you're spreading the word. Suppose there exists an element Z on this line that we're interested in, and also in the closure radius S0 of the point X, such that T is not contained in GZ. So I've motivated that somewhere along the line you'll find a Z where T is not contained inside the stabilizer. Now I'm putting a constraint. It's got to be close enough relative to the depth of the datum that I'm talking about. So I imagine that I've got some square here. This is not a super serious condition. For example, I could just say, just take those total supercuspidals where S0 is large enough. I totally forgot to tell you. So if you're correcting your notes, way back when I was supposed to say this. So you know that was part of how the depth goes down as you go along. So now I'm just saying, if this number is large enough, and I think in a lot of cases something like saying bigger than 1 would be enough to make this whole. So, but there's still some cases that we're not covering with this. So if you have this kind of point, then no irreducible subrepresentation of this Mackey component tau of G is a type. So just to say a couple of words about the proof, because it's really kind of fun. So we're looking at this K intersect GG inverse Y, right? And now let's just see where that's living. K is living inside of T GXS. This is flattening out at the very top all the way across. And then, it's still contained inside of GX. Let me just rewrite that. So that's indisputable. GX intersect GY, this is the stuff that I've written there, so it's contained inside the GZ. So we're looking at TGXS intersect GZ. And then what we've done is we've rigged it so this GXS is sitting inside GZ. So this intersection, for once, is something we can actually figure out. This is T intersect GZ times GXS. This step is usually rather challenging, but no big deal. This thing contains my TS, as we've mentioned, and this thing here is definitely not equal to T by the hypothesis that we're talking about. So I know how to pick that character psi that will make things work. So choose psi, a non-trivial character of T that is trivial on this out to GZ. If I said S, I meant S0. Triviality then, therefore the depth is less than S0 by what we've done, and then just briefly the corollary quick exercise implies that that you can construct this new datum where you twisted your first character but kept all the rest the same, gives pi psi dot such that the restriction to gy of this twisted datum contains my tau g, this Mackey component. And therefore tau g, or its twist back to be correct, is not a type. Because it shows up in two inequivalent pi of psi dot is certainly not isomorphic to pi of psi. So I have my piece showing up. The entire Mackey component showed up inside the restriction of this other supercuspidal. So there's no way that we've got a type. So that's kind of cool. I really like the picture, so we'll just hang on to it for a little bit longer. So I guess I said in words, if S0 is too small, so the case that's not covered by this proposition under this hypothesis up here, if S0 is a bit too small, well then we have two options, and both of them are a little bit messier. So one is to actually get into thinking about the Heisenberg representation construction that comes into things, which is what happens starts at S. Or another one is, we also know how, if you're past twice the depth, that we're going to intertwine with the principal series representation, or another parabolically induced representation. So there might be possible to meander and avoid too much complication here. The theorem that you can get out of this would be, since I'm only covering one case, and I haven't done the third case yet, if T stabilizes only F bar in the building. So if you have, let's call it a nice and polite torus, then that is to say that the fixed points are exactly along here. Then there is a constant C depending on this point X in your building, such that if your S0 is bigger than C, then pi psi contains exactly one type for each vertex of F, and none otherwise. And 0 other ones. And this was just a way of saying this is unicity. This is a unicity result. And that follows the unicity set here because I'm saying by my hypothesis that everything is covered by case 1 and case 2. And this constant C, this is just to come back. It's like I have to account that I might have to go all the way over here to get out of my facet to be able to finally go down to Z. And that's where that constant C is coming in, but it's clearly just a geometric thing that we would have to figure out. Okay. So this leaves case 3 if you're counting. And case 3 is the one that I spent weeks trying to prove couldn't happen. Until I came here, and then I talked with Jeff Adler, and he explains that, well, yeah, no, life really is that miserable. So this is T is contained inside of GG inverse Y, but GX is not contained in GG inverse Y. All right. So this was kind of counterintuitive. I mean, you've got this maximal torus sitting and completely identified with this point X. Why wouldn't it just be completely filling that facet? Why wouldn't you have an equivalence of these two conditions? And in a lot of cases, it's clear, like in SL2, obviously, and in lots of other wonderful cases, if my point X is inside a facet, then I'm certainly going to have this kind of condition. Certainly, I think I can take back anything that I say for certain about tori. It's a much more interesting subject than you think. But when I was searching on this, I found this thesis by Frederick Hurst at Heidelberg in 2000. 2005, and what he was doing was calculating the fixed points in the Brouhat-Heath building. Brouhat-Heath building, I don't know what I've been writing. I meant to write BGF, but it's possible I've written all kinds of other stuff, I'm sorry. So the fixed points in the building of certain, he called them primitive, anisotropic, maximal, totally ramified tori. All right. And so realizing there's a whole piece of something, you start to realize that you must have some interesting answers, and indeed they do. So he had a truly pathological example. As far as I'm concerned, maybe, but the one that I was coming here prepared to ask people about, it was an F4, and I'd like to meet the person who likes F4, and can just sit down and happily talk about F4 with me. But you can't draw this thing, and it's completely miserable. But this one, it sounds really awful. But then I was talking to Jeff Adler, and I was saying, well, what kinds of, is this real? And did I really understand this thesis correctly? Because it's 160 pages, and it's all in German. And he took margins this thin all the way around, and the font size, so it's just torture. Anyway, so I'm pretty sure that what he's describing in F4 is the kind of absolutely hideous torus I want to know more about now. But then Jeff Adler said, oh, no, you mean like this kind of example. So this is Jeff Adler's torus. And so many thanks to him for helping me walk through as, he kept telling me things, and I kept saying, no, it can't be like that. And so every step of the way, I said, no, it can't be like that. And he just, so it was great. Thank you, Jeff. Okay, so this one's in SP4. We all love SP4. And in SP4, we have SP2 cross SP2. And by that I mean your two hyperbolic planes. So this one is living on the roots 2 epsilon 1, and this one on the roots 2 epsilon 2. So this is really an SL2 cross SL2, and we really like tori in that. So for example, I can do T1 cross T2, where Ti is an anisotropic, ramified, I guess that was redundant, torus in SL2, Ti equal to T2, T1 equal to T2 would be okay for this, it doesn't really matter. Anisotropic tori in SL2, they're kind of like non-one elements of the field, but in fact there's more conjugacy classes, so there's a lot of tori here. But let's call that T. Now, this one's literally living like an SL2 cross SL2. So if you're going to draw the building for that, you would draw this as a standard apartment, and then for very obvious reasons, that point X that you're going to get has to be at the center of this square alcove. Okay, so we have this point X, and then by everything that we've understood up to this point, we realized, okay, on these 4 vertices all the way around, I should expect one type, because this is the case 1 kind of scenario. So I should have types living at these 4 vertices. Great. Now we're going to do SP4. In SP4, suddenly I have that reflection going on. So these 2 vertices are conjugates. Now what's happening with the types? So let's do this nicely. So and then also because X was at the center of this alcove, it was clear that T is going to stabilize the whole alcove and in fact its entire closure. And that still passes to the case of SP4. So this T will stabilize this entire alcove here, which means in particular that we've got the kind of case that we're talking about there. So T is contained, let me put this as Y, but GX is not contained inside GY, because those are the only ones that GX would be contained in. Let's see here. Also then with this TGS, my little condition about the S plus, well, let's just draw a little tiny square around that of any radius that's positive. It touches this alcove, therefore it stabilizes everything. So any S greater than 0 would be fine. S0 greater than 0 will work for what we want. And that means that K, no problem, is contained inside of GY, which means that what we've been talking about, that in from K to GY of kappa G is a type. Okay, so this is an unexpected place. I need to find the type. because maybe we were thinking that we'd only find them on the vertices of the facet containing X, and now we're saying, oh, no, actually, this type is living on that other maximal compact subgroup. And in fact, think about it, this is really stupid. Well, not stupid, obviously it's brilliant, but this guy here, this is a maximal compact subgroup that's smaller than those two maximal compact open subgroups, if you'll permit me. And so why is it that this smaller compact open carried that type over there? There's some things to wonder about. But this is not the worst of it. So we found a type that lived on a maximal compact subgroup that we didn't expect. And now we'll take W and G to be the reflection in this line L that I've drawn here. It's certainly an element of the affine vial group. This is going to take the vertex Y to the vertex WY. Okay, that in itself wouldn't be an awful thing, except notice that W is not an element of this double coset, the identity double coset that we were talking about here. GY times GX is not, that double coset is not equal to GY in this case. So that is to say, GY, W, G, K, when you play around with this, is not GY. I guess it's equal to just the coset with W, because K is contained. So it's enough to know that, well, certainly W is not in GY because W moves with point Y. So very clearly, I've got two different Mackey components that were at play here. And what's happening with this other one? Well, you look at the omega conjugate of T, that's just going to be T2 cross T1. I'm just going to swap the two factors, so no problem. This is contained inside GY, so T is contained inside, maybe I should have called it W inverse, I'm being sloppy. And if we do this GXX here, W is in fact contained in GX, as you can see from over there. It stabilizes the point X. So this is still my subgroup, filtration subgroup GXS0. So my K conjugated by W is contained inside of GY. And that means that if we did from the W conjugate of K to GY of the W conjugate of kappa, then this thing is a type. Whoa. So this guy is a type, and it's certainly not isomorphic for G conjugate to the one that we were expecting to find on this maximal compact subgroup, and so we have a case of non-unicity. And I guess I'll stop there.
Questions? Any hope at all to win the general case?
Oh, thank you. So yes, the general case is looking kind of neat. So certainly we can see nice arguments for if we're far enough away from the point X that our Mackey coset decomposition, there'll be pieces that actually coincide with pieces coming from parabolically induced representations. So we can certainly cut it down to at least a finite computation. Within there, what we're working on right now is the key step. Like here, the cool thing that we got to do is we took one datum corresponding to a toral, and it was super easy to just modify it a little bit and get the datum corresponding to another supercuspidal. Well, in general, we're going to have to modify something from a twisted Levy sequence. And that means thinking about this twisted Levy sequence intersected with a Levy sequence kind of inside our apartment, or at least with a parahoric inside our apartment, and that's very fun. But there's so much neat work happening out there that's reducing things to thinking about tori, that we're realizing if we just really understand the toral case, I think we're going to have a handle on the general case. Thank you. Oh.
Question. So we'll find that the argument in this hypothesis is simply correct. Obviously, it's more difficult to prove it's not simply connected. But if you could prove some kind of unicity result for a simply connected group, would that tell you something about an isogenous group and types of that?
That's a good question. So if I can figure out if it's simply connected, can I somehow go with isogeny and figure out about the types going on there? Certainly, think that there's a lot about how we're constructing the types that makes that feel like that could be a way to go. I would say that in the depth zero case, when Peter Lapham was working on that, I worked on the hypotheses as simply connected and semi-simple. But he realized that at the last step, it was fairly simple to extend to reductive and just general connected. And I forget exactly the details of what was going on. We expect it to be much more difficult in the positive depth case. But yes, about knocking off those hypotheses is the goal. And a lot of what they did for me was just to let me understand fully where all the maximal compounds were and how they're going to behave, and think entirely in terms of, well, the entire alcohol is preserved, which are shortcuts that make it much more easy to think about. But I feel hopeful that it's not horrific to tackle the best. Thank you.
No, I was just going to ask a kind of basic question which perhaps you presume that the audience would know. The question being discussed is that for a group of this kind, semi-simple, simply connected, if it is compactly induced, then the compact induction data from a maximal compact is unique up to conjugacy.
So is the data on a maximal compact unique up to conjugacy? Well, so in part, maybe we're getting to this kind of strange question. These guys are representations of GY, but they're not conjugate by something that stabilizes GY. I just know, I know that the types by JKU, and maybe that's exactly the question that we're asking, are all the types that we're going to discover conjugates of the original types that we believed were there? And this is not contradicting that. So it's an interesting non-UC result, but it's still saying that all the types we're able to discover are the ones that we expected to be finding there. Unlike that Q=2 case that Henry was talking about, where he found a brand new type that had not been constructed by known methods. This is a really obscure, small thing. But that's an accident with Q=2. Or a deep result from arithmetic. So.
Let's thank the speaker again.